Oh, is that good?
Yep, now I can hear you.
My name is Bob Cable. Currently, I'm a consultant in the CSP industry. Most of my career has been with operating facilities, and as such, I'll be discussing some of the O&M concerns that were brought up.
You're one of the daddies of Nevada Solar One as well. I think a lot of people should know that. And Bruce, you see a black box, but it's actually Bruce. He just doesn't have a camera. Hi, Bruce.
Good morning or good afternoon.
Excellent. Do you want to introduce yourself just shortly?
Yeah, I'm Bruce Kelly. I currently work for Hank Price at Solar Dynamics. I started my career in the CSP industry back in 1975 on the Solar One project for Bechtel. And I've also worked for Abengoa and Solar Reserve along the way.
Thank you very much. I'm sure Luis Crespo is on the, Luis, like these are people who've been not as long as you, but almost. Okay, so Manuel, if you stop sharing this slide, and I'll ask Mark actually to share yours, and you guys, you can take it from here. I know that you've prepared, a specific structure for this project, so go right ahead, and then at the end, we'll just, once you're done, then we'll look into the questions. As always, you guys, whilst Mark is sharing, send your questions through the Q&A box, okay? We're gonna try to get to as many of them as possible. Thank you, Mark. We can see your slide and we can hear you.
Okay, great. Thank you, Belen. And as we mentioned earlier, this group will be talking about reducing technology risk in CSP development and operations. What we're really talking about is a best practices and lessons learned activity that myself and the rest of the folks on this call and others, I'll describe a little bit later, have been working on for the past year and a half. Okay, so the objective of this last year and a half activity is to publish a best practices and lessons learned document based on for engineering, procurement, construction, commissioning, operation, and maintenance of existing trough and central receiver plants. Basically, all aspects from design to operation of both troughs and central receiver plants. Why just trough and central receivers? Because that represents almost all of the operational CSP plants in the world today. The idea behind this study is to help these stakeholders, the developers, the EPCs, the operation and maintenance crews to avoid some of the detrimental practices that have hindered some of the reliability of some of the projects, especially in the early commercial growth of some of these technologies. The audience, including some of those that I've already mentioned, include developers, investors, lenders, off-takers, basically everybody who touches CSP plants in one way or another. In addition to identifying best practices, there are perhaps some areas where there's additional research needed, and so another benefit from this study will be to identify additional areas of research, whether they're industry-related research or perhaps research from some of the laboratories around the world. So you've seen, or many of these folks are already on this particular call. I am the PI on this best practices project. Hank and Bob and Bruce have already introduced themselves, but there are a couple other colleagues that are involved in this, namely David Kearney from Kearney and Associates, Fred Morse from Morse and Associates, and Greg Kolb from Kolb Consultants. All of these folks representing a breadth of knowledge, most of them you probably recognize, a breadth of knowledge across this industry. This particular project was funded primarily by the US Department of Energy through the Solar Energy Technologies Office, but we did receive significant cost share, namely from the World Bank, this group, thank you very much, from Solar Paces, both of those actually provided cash cost share. We also received in-kind cost share from Estella and from EPRI. Before we go into a lot of issues, and you are going to hear about a lot of issues and challenges, that was the focus of this project, I do want to at least demonstrate, through some data that was provided by Luis Crespo, who we heard from yesterday from Protelmer Solar, that in fact CSP plants are operating well, especially the parabolic trough plants to date. And this graph shows The increase in performance over the years of the fleet of 50 or so parabolic trough plants that were under construction and now operational, initially through 2014, which you can see the 2014 line. And then once all of the plants were built, you see an improvement in the performance of all 50 of these plants as the operational crews have completed their commissioning and gone through their commissioning phase, and then two, improved the operation and maintenance of those plants. At the same time, and this is, I should say, this isn't actual price data, this is normalized price data, but it comes from Johan Lillestam from CSP Guru that shows the decrease in cost of both tower and trough plants over the years and projecting into the future. So it is a good time for CSP. Plant performance is improving and costs are coming down, but what we want to do in this project is to make sure that the mix of stakeholders that I described earlier have access to some of the lessons learned or some of the challenges that have been faced by many of these plants that have been operating worldwide. So we've talked to a lot of people representing really most of the plants. About 80% of the plants worldwide are touched based on the list of folks that you see up here. They represent developers, they represent the plant operators themselves, they represent operator engineers, the owners, a whole host of stakeholders that touch these plants. We've also visited a number of the plants as we've had the ability to do so, a number of both parabolic trough plants and a lot of the central receiver plants, again, that are operational around the world. And that represents, as I mentioned, 80% or more of the roughly 94 plants that are operational, at least based on our definition, are operational around the world. And I should say that we use the Solar Paces project database to identify these plants, to help us identify the relevant stakeholders. And we do appreciate the number of stakeholders who really took the time to talk to us. So on that, we had different avenues of talking to these stakeholders. We had face-to-face meetings, whether they were at those institutions or whether they were at the plants themselves. We had conference calls, we had video calls, and we also sent out surveys. And so through that mix of interactions, we developed an issue database where we've collected over 1,000 issues, challenges, best practices, representing different aspects of parabolic trough plants and central receiver plants. And we divided those, or at least developed that database using this hierarchy here. So first, we identify the technology. Is an issue specific to a parabolic trough, to a central receiver? Often an issue may be characteristic of both technologies, the steam generator, for example. We then further divided that technology into their systems, the solar field, heat transfer system, the thermal energy storage system, the power block, or some areas that we may not get into this, but at the project level, something that goes outside of the technology, really has to do with the development of the project itself. Further divided that into subcomponents, and you'll see some examples of those subcomponents later. And then for each of those issues, we highlighted a brief description of that issue. What is the impact of that issue, especially on the potential cost impact, revenue impact, or the availability impact on the plant? What, if any, what were the mitigation measures, potential solution or best practice? Then we provided both an impact score and a risk level score. And you'll see some charts that allude to that. They're hard to follow, but you'll get a sense of what we call the priority. We take the impact, whether it's low, medium, or high, the risk, low, medium, or high. That means the probability of whether that challenge might occur. Multiply those together, and we come up with an overall risk score between 3 and 25. A little bit about the report. We will cover both these topics: parabolic trough technology, molten-salt technology, O&M, and project organization and execution. And what you'll hear from today are the first three. We won't talk about project organization and project execution, although that is highly discussed in this 200+ page report. To date, the status of the report is we've had the report reviewed for sensitive information by those participants for which we were under an NDA. Once we were given the go-ahead on not including any sensitive information in that report, we went out to an expert panel. Once the expert panel provided their comments, we went out for stakeholder review, basically the list that you saw earlier, to make sure we accurately portrayed that information. And that's where we're at right now. We've received that information and we're updating the report based on input from many of the stakeholders that we heard from. And so that's where we're at. We're updating the final report, and we ideally will issue a final report at the end of this month. So I'll talk about the general findings, and then we'll switch over to each of the other panelists. Essentially, and we heard this from one of the earlier sessions that I was listening to, yes, CSP plants are relatively complex power projects. Most of the issues identified have been related to the implementation of the technology. It is by far best to work with experienced teams that just make sense, that have a proven solar track record. It's an important, and it goes along with this previous bullet, projects need to have a detailed owner technical specification, which means that the project ought to have a very experienced owner. And that owner ought to be very involved with the project itself. Those projects that have a involved owner fare better. A well-executed QA, QC, quality assessment, and quality control process in all phases of the development, design, and procurement, commissioning, and operation of the plant cannot be overstated. What we've seen in some plants, some resulting in significant downtime of the plants, is simply a problem with quality control during one or more phases of the project. One other thing we've seen is that some of the significant problems are not associated with the solar field, really, which is the heart of a CSP plant. Well, one part of the CSP plant, the other is the power block itself. And there have been problems with just conventional equipment, such as heat exchangers, valves, pumps, etc. The plants need to be designed for good reliability, and you'll hear this from Bruce maybe. It's not the 100%. I mean, it's obviously the 100% load case that one needs to design for, but you equally, if not more importantly, need to design for the 1% case. It will operate at low loads during startup, during other times, and it has to operate reliably and be designed to operate during that time. Another significant finding was the effort to cut costs up front, and we see that will end up costing the project much, much more at times in the long run. And finally, we've seen, at least in some projects, and none of these relate necessarily to all projects, but performance modeling hasn't been adequate for some projects, and especially, and this kind of goes with the 1% case, in the ability to handle transient plant behavior during startup or during intermittent clouds. Not having an accurate performance model leads to probably not reaching the performance targets that were desired during the initial decision to build the plant. So I think that covers the upfront section, and Hank, I'll let you take over. And just tell me when to advance.
Okay, thanks, Mark. So Mark mentioned we sort of identified topics we called issues that were raised by the various stakeholders. And so this chart, he mentioned that we created this priority score, which was a mix of the impact of an issue and the risk of it occurring. And so you get a score potentially between 1 and 25 based on this priority score, we called it. And then, so this chart shows for parabolic trough technology, which is what I'll be discussing, sort of a map of the higher scored scored issues. And so across the x-axis, we're looking at number of occurrences, and then the priority score across the y-axis. And so if you look in the upper right-hand corner, as you move in that direction, you get sort of the more important issues that both have a high score as well as occurred frequently. And I should point out, when we say occurrences, this is really the number of stakeholders who reported on a particular issue. So it's not necessarily an indication of the number of problems seen, but in some cases, problems were identified by more than one individual, even for the same plant. So, but nonetheless, the idea being this is a sort of a qualitative effort, qualitative approach to identify what the key issues are. And so this is a hard one to read, but basically what we'll talk about primarily are the issues that raise to up to the top and to the right on this chart. Okay, Mark, next slide. Okay, so it's important to note that there are both successes and areas where we can make improvement. And with trough technology, the general response we got back from industry was that the feeling was that most trough plants were generally working well. The solar technology is generally seen as mature. And one of the big advantages trough technology has achieved in recent years is this globalized supply chain. And so many of the unique trough related technologies, especially with the collector technology, is mature, and there's a global supply chain. And as a result, costs have reduced fairly dramatically in recent years. Okay, now there's the areas where there were issues that still remain that can be addressed. Probably the most important one that has been starting to surface in recent years is the question of hydrogen. Hydrogen is caused by decomposition of the heat transfer fluid used in the solar field. And as the heat transfer fluid breaks down, it breaks into high boilers and low boilers, and hydrogen is one of those low boilers that gets into the heat transfer fluid. And the reason this is a problem is that over time, the hydrogen can migrate through the stainless steel receiver tubes as the oil is flowing through the receiver into the vacuum space. And although receivers are designed to manage hydrogen, the amount of hydrogen that's present in the HTF appears to be much higher than originally thought. And so the question becomes a matter of lifetime on the receivers. How long will the vacuum remain? And so basically this has been an issue that hasn't been really paid much attention to in the past. And we're just realizing that it's important that we maintain the HTF, remove the degradation products. And so there's been a lot of work done in recent years looking at removal of hydrogen from the HTF through venting or membranes in the HTF system. Also, what appears to be very important is the ullage system for the plant needs to be in service and designed to remove both the high and low boilers. And then one of the other considerations is that plants ought to consider reducing their operating temperatures. Over the years, the operating temperatures keep increasing on new plant designs, trying to tweak out efficiency, but as a result, that causes a faster degradation of the HTF. And so through addressing these different issues, we think this is a resolvable problem, but it's something that each plant that's operating now has to consider how to address. The second area where there was significant concern is in the collector interconnection, ball joint assemblies, flex hoses, rotary joints. Those have been an area where there have been fairly high failure issues to deal with. Most pressing are either leaks or binding of ball joints. And so those cause problems. Those have been a fairly significant O&M expense at many plants. And basically, although the current designs can work, better solutions are needed. And, you know, designers are paying more attention to this, and I think coming up with some better designs these days. Next slide, Mark. As Mark mentioned, some of the bigger problems have been with conventional equipment. He mentioned heat exchangers, and especially for the steam generation system and thermal energy storage systems. Those are systems that start up daily. And so it's really important that you have robust designs that are designed for starting up the plant. He mentioned you need to design not just for the design point, the 100% case, but also for transient operation and especially starting up. And so this is a problem that has occurred at a number of plants, not all plants, but it's really important to have good design that protect the heat exchangers during startup. There have also been some questions on quality control of supply. These are very big heat exchangers, and so quality control during manufacturing is also very important. The DCS, or distributed control system, this is the control system for the power plant. Oftentimes it seems that the control system is not designed from an integrated standpoint, and so there's definitely improvements that can be made in, oftentimes the control systems look at individual systems like the turbine or the steam generator separately, or the solar field separately, rather than how to control the overall plant most effectively. So there's still room for improvement in the control logic. Alarm management is often a problem where the operator is inundated with what they call nuisance alarms. And so just designing the DCS to better manage which are the important alarms to show, and also automation. I think in trough plants, ironically, tower plants seem to be ahead of the game in terms of automating the system, the operation of the central receiver. And this is because it's very critical. In trough plants, it hasn't been viewed as critical. And so trough plants are operated more manually than they ideally should be. So this is an area for improvement. Finally, we think it's clear there needs to be more standards for CSP technologies. And in the case of trough plants, the structural design, how do you design a collector for wind loads? You know, it's very difficult to compare two different collectors from different vendors and know whether, you know, the designs are adequate or, you know, under-designed or over-designed. So this is an area the industry needs some standardization. And then also in collector optics, a lot has been learned in both of these areas over the last 10 years. And these are areas where industry could benefit from some standards, so there's some commonality. And just in general, most parabolic trough plants have sort of been built with the same process design over the last 10 years, you know, especially the newer ones with thermal storage. And as we sort of rethink applications in the future, there's room for improvement, I think, in the process design to make trough technology, you know, better suited for, you know, this peaker or nighttime storage, nighttime generation applications. Thanks, Mark. Oh, I got one more slide, I think. Sorry, go ahead, next slide. Keep going. Okay, and finally, this table sort of just highlights the issues in rank order. What you'll see is that we talked about the receivers in hydrogen. That was the number one. Ball joints have a couple at number 2, and number 5, the leakage and the stress issues. Steam generator design, the ullage system. On HTF pumps, seal leakage had been a problem, although it's a resolvable problem. So it's not one that's listed. It's just you need to do the right thing, use the right designs. There have been some issues with turbines, both in terms of startup curves, making sure the turbines are able to start up quickly. And some turbines had reliability issues early on. That was most of those have been related to manufacturing, and so are not considered long term. Anyway, the point here is the top, just to show that the topics we highlight as the priorities are really the top of the list. So we'll now move to a discussion of tower technology issues with Bruce Kelly.
Thanks, Hank. And so this chart is the companion to the one that Hank presented early on for troughs. Basically, it shows a number of occurrences and basically importance of a number of different topics. The ones that are the most of the most interest. And interestingly, they show problems with the salt tanks and problems with the heat exchangers as being the largest problems in these early projects. Not so much in the areas where you might expect, like in the receiver. So I'll discuss these in a little bit more in detail in a bit. Can you move on to the next slide, Mark? So some things have worked really well in these plants. And interestingly, these are the ones that might be considered the high risk items. One of the salt pumps, and the second one's the receiver. Salt pumps are typically supported above the tanks and draw suction from near the bottom. And the pump shafts here are really long, 12 to 15 meters, with power ratings, in some cases, above 1 megawatt. And so this seems like an odd design, but they've worked really well. And at Crescent Dunes, they have 9 pumps with no problems in the several years that the plant ran. Interesting performance on the pumps, not really expected. The receivers typically met its performance requirements, both in terms of thermal efficiency and other characteristics such as pressure drop, response to transients, and so on, and low cycle fatigue life, at least to the extent that these receivers have seen a number of thermal cycles. And so typically, for most of these receivers, they've worked really well. Most of the problems have sort of been in the conventional equipment, primarily in the heliostats, the salt tanks, and the steam generator. On some plants, the heliostat accuracy, which is a warranted value, hasn't really met the requirements. And what happens is the optical errors tend to be higher than what was guaranteed, which has an effect of increasing the receiver spillage because the beams are not really hitting the receiver in the areas that were expected. So if the receiver spillage is higher than anticipated, the daily and annual receiver performance then suffers. You can compensate that to some extent by bringing in the heliostat aim points toward the center of the receiver and capturing some of that unexpected spillage. The problem, though, is the peak flux then goes up. As the flux goes up, the tube strains go up, which has a knock-on effect of reducing the low cycle fatigue life of the receiver. It's possible to damage the receiver by doing this. And so there has to be a bit more experience here regarding heliostat optical characteristics and price to try to determine what's the best combination in order to provide the lowest cost energy to the plant. Regarding the salt tanks, there have been sort of 3 problems. One is that how is the flow distributed when the flow enters the tank, particularly in the hot salt tank. Most of these projects use a single ring header near the bottom of the tank, and that's where the flow is introduced. But these tanks are large. 40 meters is sort of a typical kind of a value. And so as you're introducing flows into the tank, you don't wind up with a isotropic distribution of temperatures within the tank. You wind up basically with temperature gradients. The temperature gradients lead to stress gradients, and it doesn't take much in the way of a stress gradient, something in the order of 20 to 30 degrees C, in order to establish temperature gradients in the order of 20 to 30 degrees to establish stresses that are comparable to what you'd see in like section 2 of the code. And so you have to, there have been sort of like standard approaches to ring header design, but it's not really known if these are adequate. Are you generating basically, particularly under transient conditions, stress profiles in the tank that can compromise the low cycle fatigue life of the tank? It's not really known, but some additional work is required along these lines to try to come to a better understanding of the flow distribution in the tanks and how best to control those, perhaps different ring header designs. I'm not really sure, but it's a topic that's worthy of additional research. On the next slide, Mark. These tanks are typically designed to API 650, which is a standard for welded, field fabricated welded tanks with a flat bottom and a domed roof, typically for oil storage. And these tanks are, for API 650, there's a limit on its design temperature of 260 C. So typically they'll basically marry allowable stresses from section 2 of the code with API 650 to come up with a tank design, which is okay, but for oil storage tanks, they tend to be like isothermal over the course of the year. They don't change much in terms of temperature. And so that's not the case for a CSP plant. Typically in an oil storage tank, the floor is simply there as a fluid boundary. It's not a structural element. But in a CSP plant, the tank grows and shrinks every day due to thermal expansions and contractions. And under certain conditions, you can place the floor into compression. In an API 650 tank, the floors are typically pretty thin. 7 millimeters is kind of a typical value. And there's not much buckling resistance for a plate that's 40 meters in diameter and 7 millimeters thick. And so it's possible to put the floor into compression. It's also possible to establish stresses high enough to buckle the floor and cause yielding. And it doesn't take but a few cycles of yielding to cause cracking, what was seen at Crescent Dunes. And so the tank specification has to have provisions in it to accommodate a buckling analysis to make sure that when the tank's subjected to various transient conditions, you don't put the floor into a sort of a dangerous stress situation. On the tank foundation, a lot of tanks have been built with expanded clay as the foundation material, something like Utilite, which is okay. It provides a high thermal resistance and it's a low cost material. The problem though, it's not rigid. And so as the tank expands and contracts every day, it can basically move the Utilite, particularly near the perimeter. And this can leave the edge of the tank at the floor unsupported. And at that point, there's high concentrated loads coming down from the wall and the roof. And if the tank is not supported adequately near the edge, we will wind up with basically plastic deformations of the floor. This has been seen in more than one instance. And so the foundation needs to include a rigid perimeter to handle the concentrated loads coming down from the roof. And this can be done with a refractory, either bricks or cast material. That becomes like mandatory feature of, I think, future tank foundations. Also too, a drip pan needs to be provided underneath the tanks to isolate the foundation from a leak. The thermal conductivity of salt is pretty high, much higher than the foundation material would be. And so if the tank develops a leak and the foundation becomes saturated with salt, its thermal conductivity goes way up, as do the heat losses. And that winds up being a problem with tanks. Also too, this expanded clay is a ceramic material, which is chemically inert, except that it can go from one oxide state to another when exposed to salt. And as a byproduct of that, the salt will decompose and form NOx in the form of a gas. And this happened at Crescent Dunes. It's actually quite a dangerous situation, and a few people are hurt at the plant due to NOx production coming from the foundation. So ideally, you'd like to make sure that you wouldn't repeat that situation. And if there's a leak in a in a future tank, you'd like to make sure that salt doesn't come in contact with the foundation material for whatever reason. In terms of the steam generator, this has presented some problems at a number of plants. The vendor will typically provide an allowable rate of temperature change, let's say 10 degrees a minute. It's important to stay within that limit. The heat exchangers do not have an infinite fatigue life if they have a rate of temperature change of 10 degrees a minute. And if you start to exceed that, then what happens is the fatigue life drops by a lot. And two effects. One, you can develop a failure of the heat exchanger itself, but also two, you can start to relax the friction connection between the tubes and the tube sheets if you try to operate with high rates of temperature change. And when that happens, then you develop a leak in the heat exchanger. That can be fixed by tube plugging, of course, but the downtime to do that is at least a week. And it doesn't take very many failures over the course of a year to cause the availability of the steam generation system to suffer by quite a bit. The other thing is that the process design needs to be able to control thermal loads at the 1% range. It sounds like sort of like an odd situation or odd requirement, but the heat exchanger sees this 1% low case every day. And it's important to make sure that the rates of temperature change and also the number of thermal cycles that occur at the 1% low case are under control. It's easy to have oscillations in temperature if your process control isn't tight. And this oscillations in temperature in combination with high rates of temperature change will definitely cause the heat exchangers to fail. We've seen that in more than one project. The thing needs to be done too is to control the water chemistry. It sounds like that should be like plant O&M 101, and it sort of is, but if the dissolved levels are too low and the pH is too low, you want forming rust in the condensate system that is not adherent, and flow accelerated corrosion will carry these rust components into the evaporator. And in the evaporator, if you're using stainless steel tubes, and several plants have done that, you wind up with deposits in the tubes. And then you wind up with basically pitting corrosion underneath these deposits due to galvanic action in the heat exchanger tubes. And again, you can repair this by plugging tubes, but again, you're suffering downtime on the heat exchangers. And every time you go down for a tube plugging operation, you're out of service for at least a week. And so again, it's important to control water chemistry and basically process conditions on the steam generator to make sure that the steam generator doesn't become the largest availability problem in your project. On the next one, Mark. So again, details matter. Salt valves typically have a terrible reliability and cause problems, just almost endless problems. And so the best way to deal with this is to keep the number of salt valves the absolute minimum. It does pay off in your plant operations if you can avoid salt valves whenever possible. Also, too, they have a knock-on effect. If they leak, they'll often wind up causing heat trace failures due to the heat trace cables becoming exposed to salt and then winding up with corrosion of the heat trace cables. And really, the best way to control that is to provide a bellows stem seal on all salt valves. And there's a lot of objection to that because they're expensive and they're finicky in the sense that it's easy to break them. But at the end of the day, if you can prevent a salt leak, even with an expensive component like a bellows, it pays rich rewards later on in the operation of the plant. And regarding heat trace, there's 10,000 ways to do heat trace wrong. There's one way to do it right. And heat trace installation needs to be overseen by someone who's gone through this before and make sure and can make sure that the heat trace cables, thermocouples, and every other process control element of the heat trace system is installed properly. Heat trace it sounds ordinary, but unless it's done right, it's just a source of endless grief in a project. And also too, the O&M staff has to understand the plant. These plants operate with high temperatures. They also operate with high temperature differentials. And it's possible to damage equipment very easily if you don't maintain strict control over what flows are going when. And the best way to ensure that is to make sure that the O&M staff understands how the plant runs, and how to protect the plant from damaging conditions. And finally, this is the just details on the elements that went into the chart early on in the presentation. I won't go through these, but you certainly peruse this at your leisure. But this is a summary of the principal problems and how they were ranked in the chart that was presented early on.
Thank you, Bruce. And there was the two presentations prior were kind of on the technical side. This is, I presume, a less technical matter, but common with both of the technologies. One thing that was clear after talking to the stakeholders mentioned in the project, very clear, was that the benefits of investment and proper consideration for O&M far outweighed the impacts of not doing so would cause later on. So with that in mind, one of the main priorities was that the team needs to have experience in CSP. It's not that the whole team has to have experience, but you certainly need key people that have that CSP experience. And my thought to it is this group is really the end user of the plant and who it should be built for. They're the ones who kind of take care and custody of it for a long period of time after it is built. Another important matter that was brought up was that that subject matter experts within O&M are involved early on in the project, even so much in the design, during construction, and through the commissioning period. Some of the highlights for that during construction, assisting with the QC process would help. It helps the operation team gain familiarity with the plant for when they do take over. On the design side, some O&M SMEs should be involved with the operational processes and equipment protection schemes. Bruce kind of highlighted how important the control is, but it's important that someone who's operated these plants understands the operation as part of that team that's designing these systems to make sure it's a good approach that will work. Access and workability to equipment was brought up many times by especially O&M groups as being insufficient. Operators were often, forced to access valves, for instance, that were impossible to access, and as a result, permanent scaffolding was not that uncommon. And probably a bigger concern by the O&M people, and something that they typically ended up doing later in the process, was adding the mechanisms for safe equipment isolation and efficient. It's very important in CSP to be able to efficiently evacuate systems so people can start working on them. And oftentimes that is not considered in the design. And as well, it's important that the O&M group is involved with the documentation that's provided by the EPC, especially in particular the O&M manuals, procedures, drawings. It's very important they're involved with that process. Next. Well, this is a little, okay. Another consideration is the cost for O&M. It was brought up that these typically are not budgeted correctly. Some of the things that were brought up as not being considered properly was the equipment degradation. That needs to be kept in mind. A big one was the pay structures for the personnel. They need to be competitive with, rates in the area, and power generation is a good comparison. It's a similar technology. And there's also a lot of regional conditions that need to be thought about when these estimates are being done. And another factor was the remoteness of projects and how far, how reliable, how experienced are the service providers in the area, and how do you staff appropriately to address those potential issues. O&M, the preparation of the O&M team is very important. And again, the sooner the better. The mobilization, the quality, and training are all important matters. And the O&M group, it was thought they can't rely specifically on the EPC's training. They need to go in with an attitude to work with the EPC and also develop their own training. So it's kind of a joint effort, but it's important that the O&M team, is aware of that and has a system in place to train people. I think I mentioned it earlier, but again, they should be involved with the development of the O&M manual and procedures. And if not the development, at least the review and approval process. The people that operate the plant should have a hand in that. And another important consideration is that the plant systems are in place. Certainly the safety and environmental programs need to be addressed. Spare parts and inventory, first of all, are the spare parts adequate? And that needs to be looked at, by people experienced with the technology. And is there a program that properly addresses the concerns of the spare parts and inventory? Maintenance programs were brought up fairly frequently. Is not always, when I talk maintenance program, I'm talking like a central maintenance management system. And it was brought up in several cases that these systems often were tailored to financial programs and not so much maintenance programs. And as such, they were not as effective as they could be. So it is an important consideration to what kind of system you are using. Other considerations that were brought up, they tie into some of the other things, but it's again, it's very important to bring people in early. That's a huge thing. And what this first bullet is meant to be is, this is kind of when O&M takes over, that people with the O&M skills, the engineering skills, should be considered for a period of time. And it's hard to define the period, but that expertise should be accounted for some period of time while the project is still kind of being learnt, and eventually that would go away, but it needs to be considered. The KPIs are important. It's not just important to have KPIs, but they need to be well defined and then be monitored and used throughout the organization to have meaning. So I just wanted to make that point, that the relevance of the KPIs are very important. There needs to be a very rigorous and continuous training of plant O&M personnel. And that's the deal. You need backups, and as well, attrition has been issues in other facilities. So the better people are trained throughout the organization, the better you're able to deal with those kind of things that will inevitably happen. And as Bruce brought up, and probably one of my favorite issues is water chemistry is so important to these projects. And it was such an important consideration. There's a whole section in the report that kind of deals with how important the water chemistry is. And lastly, there's a slide. This is just kind of a summary, but it kind of shows the things I went over. And these were the kind of the highlights of what came out with our discussions with the stakeholders of the project. And again, you can look at this at your own leisure later on.
Thanks, Bob. Belen, I know we're at our time right now. If we could go maybe 5 minutes over.
Yeah, absolutely. Go for
I think
it.
what I'll
You had a
do is-
bunch of questions, so.
We do. So, I've been tracking some of them. What I'm going to do is leave this conclusion slide up. People can read those conclusions, but I'll go right to some questions, if that's okay. So there was a good question. It kind of came up briefly, I think, during Hank's presentation. But one question was, is there an international standard, especially for the CSP equipment? We might as well talk about the Parabolic too. But are there international standards for CSP field equipment, whether that's towers or troughs? Any one of you can take that on, probably Bruce or Hank.
The answer is sort of no. I typed out a response to that, but ideally that would be encompassed in the owner's technical specification. And unfortunately, a lot of those are proprietary, either to the owner or to the EPC that worked on the project. Ideally, you somehow compile the information and all the owner's technical specifications from over the years, put it together in one document and release it publicly. And that way the experience from previous projects, both good and bad, could be rolled together into one document, shared, and then spare future engineering contractors from making the mistakes that were made on previous projects. How you do that, I'm not really sure, but that would be the ideal situation.
Hank, anything to add?
No, I think this is one of the areas where I know a number of, I believe Spain has worked on some, and I believe China is working on some, but I'm not aware of any international standards, and it's clearly something that's needed.
So Spain through ANOR has been working on standards. I think you mentioned international, the IEC. I don't know if those have been released, and yes, China is working on standards. I think it's also worth mentioning that within Solar PACES, while Solar PACE, IEA Solar PACES does not develop standards, they do develop guidelines based on expertise within the Solar PACES community. And sometimes, or often, I guess I would say, those guidelines make their way into standards, or at least into the standards process in Spain or other communities. Another question, I think this is for Bruce. What is the allowable heating rate for a central receiver during startup? If you have that information that you can share, and what is a typical delay you would find during startup?
So for preheating the receiver empty, the heating rates are pretty low. You're relying on basically on thermal conductivity to handle that. And so there's not really a heating rate, but to go from ambient to, let's say, 300 degrees probably takes about 20 minutes. So the rates there are pretty low. Under transient conditions, once the receiver is filled and flowing, it'll tolerate 6 degrees a second and 30,000 cycles at that rate. So those are really robust designs and can accommodate huge transients. In contrast, a heat exchanger like for a steam generator is probably like 10 degrees C per minute. So those are kind of typical rates that are seen in a commercial plant.
Thanks, Bruce. Good question here for Hank or for Bob. Damage rates, I think that, well, this is specific to Trough. So damage rates for, I guess, current damage rates for mirrors and the HCEs, the receivers in parabolic trough plants, yearly, let's say.
Well, I think, I'm not sure I know on the mirrors, but the receivers, I think people reported anywhere from 0.1% per year up to about 0.5% per year. I think Bob's plant at Nevada Solar One has had the lowest receiver failure rate I've seen, which was probably 0.05% a year or something. So it's a well-designed plant. The receivers failure rates can be very low if well-designed and operated. On mirrors, I'm not sure I have the correct numbers on mirror failure rates. It depends on the type of mirror. The new mirrors, forgetting the type of glass, but the new
tempered glass.
What's that?
Tempered.
Yeah, tempered mirrors. Failure rates are very low. I think early on we were experiencing failure rates. Well, I think the failure rates are very low on the tempered glass mirrors. In fact, most of the breakage of the mirrors is now caused by receiver failures. I think, short of receiver glass fails and might take out a couple mirrors, but mirrors themselves are very strong. The tempered glass mirrors. So, Bob, do you recall the mirror breakage rates? I think they're also in that same range of like 0.1% a year is sort of the expected level. Yeah. Anything above that is probably there's an event or something that causes failure, but that's not real common.
Okay, I think we're basically out of time, Belen. I do want to draw people's attention to a couple of these conclusions that I think are worth mentioning, and that's really the first and the last. We do believe, the few remaining technology issues that we've described here, they're design issues, and they can be resolved, with an adequate engineering and equipment selection, with a good, solid team with experience. These can be resolved, and based on that, from our understanding, from our discussions with the stakeholders that we've talked to, that we are confident that future tower and trough projects can be built on time. We didn't talk about schedules, but on time and on budget, and to perform as expected. I think those are very important items to take from this presentation and from the study. Again, I will say that the study is over 200 pages. There's a lot of detail that goes beyond this. It will be available soon, and I hope you can reach out, especially to the solar dynamics teams, if you have questions here, more than questions, but hopefully you can reach out to this team to dig into a little bit more detail on some of these best practices. That's it, Belen.
Thank you very much, Mark. I also wanted to do a shout out for Fred and Dave, who are part of your team and are also in the audience. And I actually wanted to ask a question, but it's a rather funny one, maybe. You guys have been all working in the CSP industry as long as you care to actually remember. I mean, is there anything that surprised you, in the findings of this report? Is there anything you went like, oh, wow, I didn't expect that?
So if Fred and Dave were on, I mean, yes, and it's a great question. So we expected to hear a lot, and we did hear a lot about technical issues. What we didn't expect as much were the project, what we call the project issues, contractual issues, initial development issues. Those were, we heard a lot about those, and then that probably represents 30 to 40% of the input we received in the report. We don't ignore that in the report. We just didn't have time to get into that here. And we will certainly do that for future webinars. And I should say that with the Solar PACES funding that we still have, we plan on additional webinars. We may have a workshop at the next Solar PACES symposium, which will be held down in Albuquerque this year in the US. And we'll find other avenues, perhaps through the World Bank, for additional venues.
It's quite interesting, isn't it? How like the obvious thing that you think would work because we know how to do it is where the lessons learned are. This is really interesting because like most of you, all of you actually have a lot of experience actually running this kind of projects. So I would assume that you guys found that it's very challenging in such a large scale.
Yes.
Yeah, more so than
Bob,
the technical.
Bob or Hank, you want to?
Yeah, Bob, go on. I want to hear from Bob.
Yeah, I mean, I think a lot of the problems are common though, Belen. And I think one good thing about this report is hopefully it'll spur further participation with people and share the knowledge amongst others. I mean, there are certainly a lot of common issues going on, and I think it's good that the community kind of works on these things, and hopefully this will be a springboard to that happening.
I mean, there's always a lot to learn for sure. I read this article once that the hospitals learned a lot from the air industry, because the list of procedures that they had helped them actually make a lot better their own running of their systems or their hospitals. So they can always a lot be learned from other industries. All right, you guys, thank you very, very much. Thank you to Bob, Hank, Bruce, Mark, also the people who are on here, Fred and Dave and Greg for this great study. We are done for today, guys. Thank you very much for consistently being there. Thank you very much for the questions, for attending. I am sad that this project is finishing, quite honestly. This was the World Bank MENA CSP Knowledge and Innovation Program, and this is the capstone event. But at least what we have is this recorded materials. You can consult them anytime. You can look at the recordings again. You can look at the materials. So we will send those next week. And other than that, just literally to say thank and say goodbye to everyone and see you next time. Bye, guys.
Bye.
Bye.
Bye.